So the charge of Q2, I call it QT. QT means the test charge. QT, the test charge. The test. It is a sensor charge, test charge. QT is test charge. Test charge. So to calculate the field, you put a test charge of 1 plus 1 there. Of course, the units will be coulomb, distance, arcs, meter, and so on. You can't use cm here, inches there, micron there. No. You must use MKS unit, rationalized meter, kilogram, second units. Okay, so we move on to the field. So now, in general, as I say here, if you want to be distribution of charges, if the charges of the density of rho, which can vary with distance, then I can calculate the field upon P. Again, to do this, I put the test charge of plus 1 there, QT there, plus 1, and I subdivide the volume of charges into many kinds of delta V, volume, and using calculus, I calculate the force for the charge, of course, distance, the angle will be taken into account. This will be the field. So the principle is the same, but except that now the distribution of charges is far more complicated. So what? Makes no difference. But of course, when you do this, when you integrate this integration has got unit vector r from here to here. It varies, as you move around this, the r will vary. So it's not so simple as it shows here. Right? For a small element, delta v, the vector r is like this. As you move around the delta v, vector r this way, this way, this way, this way. So it's all complicated. Just now. Unless you have not been following. Here, suppose this could be part of some body here, some body, you can see. Here, the vector r is this way, the vector r is this way. As you scan over the volume of charges, you find out the field, the vector r changes. So this simple, this straightforward thing, simple expression is not the real story. The story is far more complicated. You have to set up the coordinate system, say x, y, z. Again, calculate the force on the charge at plus 1, get the field in terms of ax, ay, az. If you use x, y, z coordinate system, and that will be the answer. But it's not that simple. It's not that simple. But the principle, PLE, principle, PIN, CI, PLE, is the same. Yes? You learn the principle, the concept, and you can apply any problem. But coincidentally, when you read paper every day, you can pick up 5 to 10 mistakes. For example, they say, the principal of the school, PLE. How can it be principal of the school? Principal, PL, the headmaster. Right? You don't know. I say, this is with regards to. With regards to. As I'm sending you regards. This is regard to. This is in regard to something. This is as regards something. All those people writing newspaper, oh, rubbish. You're writing, it's called journalism, but you don't even know how to write things. Sometimes you write to me, you don't understand what I'm saying. Have you seen a TV program about football? I watch football, about football. There are 5, 6 matches, different channels. They put, the way they put it, you don't know which channel is which. Because they don't know how to use punctuation. Comma and then semicolon. They know, all commas everywhere. You don't know what they do. Okay, so therefore we are saying that we have to calculate the field when the thing is much more complicated. And later we shall see that this method of calculating electric field from a from a charged body is a basic method, but if the charged body has symmetry, then things can become very simple. Can simplify. That's why later we shall see, when we talk about Gauss's law, which exploits symmetry. So this one I leave for you.
Times 1.
So now let's look at the next problem, which is here. This problem is the same as in the tutorial.
这个是保证把它在那边就变成 multiply， 我也不懂为什么，给我们。
Tutorial is done again there for you. So this is a coordinate axis x, y, z. X, y, z form a right-handed set. You take x, cos y is z. So when you choose coordinate system, you better make sure that your coordinate system always form a right-handed set. Other reasons. So this loop is a charged loop, like a hula hoop, like a ring, is charged up. The radius is A. Okay. The charge density per meter is lambda coulombs per meter. Okay. And the question asks me, calculate the electric field at point P at the distance of Z along the axis. This is the axis. Please follow. You have it in front of you. Please follow. So the first thing I will ask ourselves is, can I use Coulomb's law directly? The field upon the charge of +1 here. I take the charge, multiply, get the answer. No, because this is not a point charge. I can't. So I have to subdivide this ring into small element of charges. So I divide this ring into small element of R, which is delta L. Delta L, calculus, trigonometry, A delta theta give you the L. So the small element of the arc of the circle, which you are supposed to know, is simply radius times angular radius. So angular radius delta theta, so it is A times delta theta. So therefore this small element here is given by A delta theta, it is A multiplied by lambda, so this gives me dq. So the dq is given by A delta theta and lambda. So we are getting dq. Okay? Now we can see what I do now. We are going to calculate the contribution of the other point P. We put a test charge of +1 there as usual. This charge is a positive charge of lambda A times d theta. The distance is given by here. This is Z, this is A. This distance is A squared plus Z squared. Pythagoras theorem is 90 degrees. Therefore, I have R. This is R here. So therefore, I can write down now my first expression. The electric field due to the small lambda A, the dq, lambda A d theta, is given by the charge dq or lambda A d theta times 1 over 4 pi epsilon r squared. R squared is given by this distance here. This is a right angle triangle. This is A. This is Z. This is given by A squared by Z squared. Square root over the missing one. A squared by Z squared. Okay. So therefore, I can find out the first contribution here. Now this first contribution here will be this way, and this is a vector, has got two components. One component parallel to Z, and one component 90 degrees to Z. Okay. The DE consists of two components. DE1 cosine of phi, but then in order for me to explore the symmetry, I choose another element diametrically opposite the first one. So lambda A d theta across here. Why I do this? You will see why, because then there will be some cancellation. So this contribution is DE1, this contribution is DE2. There you can see they're the same, I've got the same magnitude. Therefore, when I resolve along Z, I have DE1 cosine of phi, when I use right here. d into cosine of phi, and then 90 degrees, I think they cancel because d1 sine, d2 sine, d1, d2 the same, that's what they cancel. So therefore, the contribution of these two rings here, two small elements, is simply given by 2 times lambda a times a d theta divided by the distance, but and the whole resultant is derived from z.
D dito, I think.
Because this vector here they cancel here. Now, before I jump to conclusion, don't forget, I can find out what is cosine of phi, cosine the adjacent over hypotenuse, Pythagoras theorem, z over root of a square by z square, which is here. I plug in there cosine phi, I get the answer here. But I have to be very careful now. I am not integrating respect to z, I am integrating respect to theta. Because as I scan over this ring, whatever be the value of z, it doesn't change anything. The integration at the source doesn't change. You are looking at the contribution of each one of these elements. So it is integral of the whole with respect to theta. The whole stuff here is a constant. So all these things just come out. This one doesn't do anything. Just integrate only d theta. You are okay with it? This whole thing do not depend on theta. Not dependent on theta. Therefore, I integrate d theta. What's the integral of d theta? What is the integral of d theta? Surprisingly, a lot of people don't know that, you know. What's the integral of d theta? Why? So, calculation of the learn. Integral of d theta is theta. So, theta goes from 0 to, not to pi, because you have taken two elements together. Theta goes from 0 to pi, not to pi, because as it's 0 from pi, you have covered the whole ring already. To cover the whole ring, contribution, theta goes from 0 to pi, not to pi. If it's 2 pi, you're double counting. Think, focus. As you move theta to 90 degrees, theta to 90 degrees, the other one has scattered. Okay? So therefore, the whole thing is a constant, finally becomes theta. Theta 0 to pi, you see pi here on top, pi and pi cancel.
I think QT Z plus 1. See?
Again, you have to think what you're doing. So, if I choose Z, say 50, my integral don't, the d theta don't change. I say Z 100, everything is the same. The field changes, but the integral always respect to d theta. Now you think about it, you ask yourself the question. This complicated expression is inviting you, if you don't think, to integrate it. You don't need to integrate it. Because this whole thing, you are scanning the across theta, across the source of the charges. This is the source charges. You're looking at how the contribution adding up from each element. Nothing to do with the distance z, nothing to do with it. I can put a point P somewhere here, that doesn't change, the theta doesn't change. It's still the same thing. In other words, I am integrating with respect to the coordinate of the source of charges. So, the z doesn't come in. You can try z 50, do the calculation, z 1000, do the calculation. Still answer is pi on top there, 0 to pi. Right? Nothing to do with z. So that is why it's more advanced world. When people are calculating field due to some complicated system, they have two kinds of coordinate systems. Something called observation point, forces as P. The coordinate systems are X, Y, Z, like here. But the coordinate system for the source, like here, they don't call it X, Y, Z. They call it X prime, Y prime, Z prime, and they call it theta prime. So that we don't mix up. This is more advanced. But you can see the angle theta belongs on the ring as you scan, but the angle phi doesn't belong on the ring. The angle phi doesn't. The angle phi is determined by the point P. As you move P along like this, you can see here. Cosine of phi is Z A squared plus Z squared. When it depends on Z, doesn't depend on the source. Right? The theta doesn't depend on Z. Nothing to do with it. Okay, let's move on. So therefore, after I do the calculation, this string remains the same, no change. Integrate 0 to pi, d theta becomes theta. Theta 0 to pi becomes pi. Pi cancel pi, the bracket give me a lambda 2 epsilon naught z over a square over z square 2 by 2. So you see that the auto integration of z is the same. Now, so that field is pointing in direction. Okay. But of course, there is symmetry there. The field also down here. Also this way, in this way. Because the ring is symmetrical. But we are not asked to calculate this way, we are asked to calculate this way. So think. So now, let's check whether the answer is correct or not. Does it make sense or not? So, if I take the point P, I go very, very, very far away from the ring of the charge. In other words, when Z, distance Z is much bigger than the radius A. When Z is much bigger than radius A, I apply a limiting max. Z is much bigger than A can be neglected. So I have Z over Z cube. Z is Z cube, Z square. So finally, you can see, I found out that the limiting form of E for Z much bigger than A becomes Q over 4 pi epsilon Z square, where Q is 2 pi A lambda, because this loop is 2 pi A. The concurrence times lambda, the total charge 2 pi A lambda. So therefore, it's as if I have a point charge of strength 2 pi A lambda at a distance of Z very far away. So it is 2 pi A times lambda multiplied by 1 over 4 pi epsilon Z square, which is here. So therefore, the answer is correct. As you go very far away, that ring appears to be a point. When Z is much bigger than A, you find that it's as if the whole ring of charge is 2 pi A times lambda, which is Q. Very far away is Z, so therefore it is 2 pi A times lambda multiplied by 1 at the point P very far away over 4 pi epsilon Z squared. It's here. Z is bigger than A. Okay? Think. Are you asking anything?
No. I just come to
Okay, so we have seen already how the calculating field from, first of all, we have to do the first one there, calculate the force in there. So you can see this Q times 1 over 4 pi epsilon squared, and this is straightforward. And of course, with the vector, you have to do the maths properly. So let's now look at another example which is given to you here. Look at it yourself. See whether you can figure out what it is. I have a line charge, lambda coulombs per meter. Since the line charge is not a point, I have to chop to small elements. So then chop coordinate element dx. Choose my coordinate system x discrete. It's up to me. I don't have to go to the right, I can go to the left. So here the point P, I want to fill the point P. I put this charge of +1, 2P, +1 here. What is distance d0? To me. I have to sum the contribution of those small element of charge dq. dq is equal to lambda times dx. Lambda is coulombs per meter times meter, give you coulombs. Units will be correct. Remember this. To check that the formula is correct, always must check the units are correct or consistent. If the units are not consistent, forget it. You're wrong already. So dq times 1 over 4 pi epsilon d0 plus x squared give you the contribution dE. When this you can see the force acting is repulsive, assuming positive, is going to the right. And here minus x is pushing this way. So finally, I have the contribution. I want to find what is the total field of the point P. Since that all the elements are pointing in the same direction, therefore I can simply add them together. I can break it.
学到这个根本就会那你等，因为滴都变成滴头，
All the vectors do the
你找
same
不到滴
direction.
头，
So add them together.
对，那你再扫那个拍进去的地
So
方，
integrate from x equal to 0 to x equal to L.
你就 cancel out，
Do the same here.
เอาคนนี้ดูทันละ
Integral of 1 over d0 plus x squared. Okay, integrate. This one, no problem. Minus 1. Integral of 1 over x squared is the same as minus 1 upon x. You differentiate this, you get this. Substitute. Finally, you can see now, very, very far away. Very, very far away. If d0 is very, very large, if d0 is very, very large, respect to L, then this L can be neglected. Answer will be lambda L over 4 pi epsilon naught d0 squared. So when I go very far away, the line charge appears to have a point charge and a point charge of strength lambda L. So lambda L very far away, point P is +1, so field is +1 times lambda L divided by 4 pi epsilon naught square. What is our square? We are very, very far away. We know square because this is bigger compared to that. That's the answer. So this is a simple problem. If I make it more complicated, I ask you now, what would be the electric field on the perpendicular bisector of this line charge? Or what would be the electric field at an angle 45 degrees offset here? So the answer is, so what? No problem. Same principle. Of course, I've applied our maths, which I hope is not shaky. If it's shaky, forget it. It shouldn't be here. So you need maths. Maths is the easier tool. And maths actually is God's gift. The gift from God. God's depending on him. The gift maths. Okay? So now you have seen how to calculate the electric field of simple geometry. But you can see here now a line source, depending on how you choose it, this is simple to calculate. If I had an angle, what happens if I had to calculate an angle here? I still can do it. I put the coordinate axis. Again, I subdivide, I calculate the various R. I resolve each component into vertical and horizontal components. And I do the same thing. But I don't know whether you really have thought about it. When people add vectors together. Actually, they can't have vectors together. Right? You cannot have two vectors together because vectors are different directions. But the beautiful idea is that, concept is that you can add vectors together because you can resolve each vector into fixed direction space. In other words, x and y and z. X, y, and z are fixed. Therefore, I can resolve it around x, y, and z components. X component don't change direction, I can add them up algebraically. Y component, I can add them. Z component, I can add. This is how vectors are created and dynamic. I don't know whether you realize that, I'm not sure. Did you realize this? Did you realize this? Vectors cannot be added unless you have resolved them into fixed direction space. In other words, x, y, z, these are fixed. Okay, so now we go further. 5 minutes. Now we look at how electric field can be pictured. I can be viewed pictorially. Pictorially. Picture. So before we do that, let me just refresh your memory what we said. Electric field at point is calculated by setting the test charge of +1 on the point, calculate the force on that point, on that test charge. In other words, electric field at the point, E vector, is the value of the vector, the value of the quantity, volts per meter, that indicate the magnitude of the field and the direction of the field. Magnitude, direction is the vector. So therefore now, you can see now by, if you want to know what's the direction of the electric field or what's happening, you put the test charge of +1 there. By calculation, if it is positive, it's going to repel. If the field is negative, it's going to attract. So in this case here, look at the simple picture. You can visualize. So the density of the line is what's here. Okay, suppose this is the electric field, E1, E2, E3. So in other words, you can see that the electric field, if you put the test charge of +1 here, it's going to be pushed to the right, push to the right, push to the right. In other words, electric field, we know the force. The value of electric field means the force acting on test charge. So let me show you some pictures now. How you can represent the field. If the field is very strong, you can represent by means of density of the charges. Some of you have seen, I don't know if you have seen or not, if you take a permanent magnet, you dip it in the iron filings, iron is being attracted by the magnet, so therefore you can see then the poles, north and south. The iron filing concentrate. In the middle, magnetism is very, very weak, no iron filing. I don't know whether you remember this or you can visualize this. Okay, magnet here, magnet here. North, south. So you dip in iron filings. Iron filing means powdered iron. Iron is magnetic, so therefore you can find that this thing will concentrate here. Here, nothing much. So therefore you can see this gives us an idea of the picture. Where the field is strongest, the density of the lines of the iron filings are the densest. Same idea. Okay. So, for example, this one here, if you look at this picture, first picture is concentrate. So the number of lines leaving a positive charge or approaching a negative charge is directly proportional. So the more the lines, the stronger is the charge, the stronger is the field. For example, this one, look carefully. If the charge of +1, if I put the test charge here, it's going to repel. So the direction of the electric field, as you can see, the direction in which you put the test charge down there is going to repel. You can see what? +1 here, +1 here, +1 repel. If it is minus, you put a plus 1 there, test charge, it is right. And you see, please look at the direction of the arrows. Negative charge. Now, another picture. Arbitrary, I counted. For plus 1, 1, 2, 3, 4, 5, 6, 7, 8 lines. Okay, charge of plus 2 will have 16 lines. You count 16 lines. Of course, does it have the 16? I can put 5,000 and 10,000. The ratio of 2. This is the arbitrary picture.
那离底都是 constant 的，其他的这个离底的，他讲是
The
constant，
charge is twice the amount, the number of lines.
所以他讲不用管，只是管那个
Of
x。
course, number of lines will be x times twice x. Does not be 8 and 16. You're going to stop if I didn't want to damn it. No, they're going to have a break down on the chat. And this will be fine.
有这样吗？
Wait. So now, last thing. Carefully, plus 2, you can see the lines. Lines of electric field always come radiate from positive. Lines of electric field always radiate from positive charge. Lines of electric field always go into negative charge. Okay. So therefore, we will start. If you look at this picture here, I have a charge of plus Q and minus Q. Plus charges radiate out, minus Q go into it. But you can see start from there and then there. But you can see, look at this picture again. We say two charges have got opposite charges attract. If you look at this picture, it's as if these springs, loaded spring, trying to pull. So lines are effective and pull the charges. So if you look at now, the charges are opposite sign repel. You can see the lines are effective. Cannot cross, cannot do it like this. Here like that. Plus 2, minus 1. So plus 2Q, minus Q. You can say number of lines that come out from there. Half of it will end up here. The rest will be finished. In other words, with the charge of minus Q at infinity. Infinity is a very convenient way of getting out of a difficult spot. Because according to charge conservation, if you create a charge of 5 plus 5, somewhere somehow a minus 5 will be included. Because the total charge in the universe is always fixed and change. And change, all the same. So if you create plus Q, where is the minus Q? Minus infinity. Okay, so we stop here. Please go for your whatever it is. Come back. Please come back.